here's what I want to say first of all. You shouldn't be worried too much about having to solve differential equations. I know we talked about that in class a little bit today, but really what we're doing is we're only really worried about this specific differential equation. Dx dt equals a times x. And then he showed it in class, and the way he kind of went about it was a little bit different. You can certainly do it the separation of variables way, but really you just need to be aware that if you're looking for the derivative of x with respect to t equal to a times x, or you could write this as, and he wrote it more as d dt of x of t is equal to a times x of t. Just trying to be super duper explicit about the fact that x is a function of t. If you write it that way, it's even more clear that, well, maybe not more clear, but what I'm trying to say is that the solution to this differential equation is x of t equal to the function constant times e to the at. And the reason that's true is because you take the derivative of that, the derivative of a constant times e to the at is the constant times the derivative of e to the at is e to the at times the derivative of at, and the derivative of at is just a. But this here, this c times e to the at, that is what x of t is equal to. And so that's x of t times a, which is just a times x. So the derivative of x with respect to t is a times x. The questions about that. Then he also pointed out, right, if a is greater than 0, you've got growth. If a is less than 0, you've got decay. Yeah. And you can find the c value if you know the initial condition. So that c value is your x naught, which is just x of 0. Which is not super duper important. And I think that's all I really want to say about that before we get into where we're really going with this. Okay, so we're going to take it back to 17b a little bit. In fact, someone asked me to go over questions 3 and 4 from the worksheet. I'm not going to go over them exactly, but I am going to do some problems that are very, very much related. So for the person that asked me to go over questions 3 and 4, what we're about to do is essentially the same sort of work. So yeah, and maybe we'll do an example that's more like that specifically, but let's go ahead and start with this. So a lot of this class is based around finding eigenvalues and eigenvectors with 2x2 matrix. So let's look at some examples. Let's say we've got the matrix. What do we got here? -1 to -3, 4. And I want to find, we're just practicing, right? We're practicing, we're reminding ourselves, oh yeah, how do we do this thing? How to find the eigenvalues and eigenvectors? Because you're going to be doing this a lot the rest of the quarter. So we're going to find the determinant of a minus lambda I, and we're going to set that equal to 0. So that's going to be the determinant of, let's see, -1 minus lambda, 2, -3, 4 minus lambda equal to 0. The determinant is this times this minus this times this. So that's going to be -1 minus lambda times 4 minus lambda minus 2 times -3. 0. Multiplying this out, I get, let's see, -4 plus lambda minus 4 lambda plus lambda squared plus 6 equal to 0. This, I rewrite this as lambda squared minus 3 lambda plus 2 equal to 0. Usually, no, I wouldn't say it. A lot of the time, these are going to factor nicely. Some of the times they're not. You're going to get terrible square roots or even imaginary numbers. You are going to get some imaginary eigenvalues this quarter. But this factors nicely as lambda minus 2 times lambda minus 1. So our eigenvalues are lambda equal to 1 and lambda equal to 2. Briefly, I want to tell you a quicker way to do this, which is especially nice when the eigenvalues get kind of gross. Like for nice integer values like this is fine. But sometimes they're going to be gnarly, like imaginary or just irrational. And so there's actually a quicker way to do this. So if you look at this matrix, there are 2 properties of this matrix that you should be aware of. The trace of the matrix A is just the sum of all the diagonal elements. So it has to be a square matrix. It's going to be 2 by 2. You're just adding up the diagonals, but it's true for any matrix, right? Or any square matrix. Like if you have a 3 by 3 matrix, the trace of that matrix is all the diagonal things added together. So the trace of A, which we usually use the Greek letter tau, it's just the sum of -1 and 4. And the determinant of A, which I know you guys know, right? The determinant of A, which we often use the letter capital delta for. These are the symbols that are used in your book. Is that we know how to define the determinant of a matrix, right? It's -1 times 4 minus 2 times -3. So it's -1 times 4 minus 2 times -3. That's going to be -4 plus 6, which is 2. So here's something I really think is worth your time to remember. When you find this equation, what it actually works out to be, and this is always true, is that right, when you're finding the determinant of A minus lambda I, you're going to end up with lambda squared minus the trace times lambda plus the determinant. So hopefully you guys can all see that, right? In this equation there, I exactly got lambda squared minus the trace plus the determinant equal to 0. And that's always true, right? If you've got a 2 by 2 for a 2 by, I think it's actually, no, for bigger matrices, you got higher powers. For a 2 by 2 matrix, this formula is always true. That if you're finding the eigenvalues, you're really solving the quadratic equation, lambda squared minus tau times lambda plus delta equals 0, where tau is the trace and delta is the determinant. But then we can use the quadratic formula and say, okay, that's going to mean that lambda is equal to, so my A value is 1, my B value is -tau, and my C value is delta. So that the eigenvalues are given by, let's see, -b, so tau plus or minus the square root of b squared, so -tau squared is just tau squared, minus 4 times A times C, so 4 delta, all over 2. This may look more complicated at the moment, but I promise you, this is worth your time to remember. So if you're trying to find the eigenvalues of a 2 by 2 matrix, you can find that the trace is whatever it is. The trace here is 3, right? -1 plus 4. The determinant is product minus product, which is 2. And then the eigenvalues are just the trace, which is 3 plus or minus the square root of 3 squared minus 4 times 2 all over 2, which in this case is 3 plus or minus 1 over 2, which of course is 2 at 1. You don't have to do it this way. You can totally do it this way, where you do the determinant of A minus lambda I set it equal to 0, write the whole thing out. But this is actually, I think, easier. Okay, enough sales pitch for that method. I will refer back to this method. So we'll definitely, the thing that's nice about knowing this is that later on, we're going to talk about categorizing our solutions based on what our eigenvalues look like. And it's really dependent on what we know about tau and delta, the trace of the determinant. So if you're able to see it this way, you get to be like, oh, I can see that tau is positive and delta is negative. I know my solution is an inward spiral, or I know my solution is a sink, but I know those words don't really mean a lot to you yet, but they're going to. So again, I will say one last time, probably not really, I'll probably say it a bunch more times, but I really encourage you all to practice this, and we will do it in the other ones we do later on. So we're going to find the eigenvectors now. Eigenvectors, there is not a slick way to do it. We still have to do what we've always done to find eigenvectors of a 2 by 2 matrix. So this lid screwed on tight here. So right, to find the eigenvectors, we are going to say I want to solve A times V equal to lambda times V, right? The eigenvectors are the V's. We know the matrix A, we know the value is lambda. So that's your eigenvector is a vector. So we're going to try and solve A, which I forgot what it was already. It's -1, 2, -3, 4, times the eigenvector that we don't know. And it's pretty typical to use x and y or x1 and x2. I'll use x and y, although I feel like the professor's probably going to use x1 and x2. I don't know. I don't know really. And then we have to pick which eigenvalue. So let's do lambda equals 1 first. So lambda equals 1, that's going to equal 1 times xy. And remember, so we did a lot of this last quarter. And remember, we usually just use one of the equations. So I'm going to do -1 times x plus 2 times y equals 1 times x. And then I think in Karana specifically, how do you guys like solve for y usually? So you could draw the line. So if we solve for y, we get 2y equal to 2x. We get y equal to x. And then you have to pick a number for y or for x. Pick the smallest thing that makes it not a fraction. In this case, except for 0. We don't pick 0 unless we are kind of forced to. So what I really should say is, if you pick x equal to 0, you can get y equal to 0, and you're never allowed to have the 0, 0 vector as an eigenvector. Anything else is fine. 0, 0 is never an eigenvector. I really emphasize that, right? 0, 0, never an eigenvector. Anything else, totally fine. So pick x equal to 1, you get y equal to 1. So our eigenvector is 1, 1. And let's call this the first. Let's say this is lambda 1 equals 1. So this is v1 equals 1, 1. Sometimes, like this one, the numbers happen to very nicely correspond. Right? My first eigenvalue is 1. My second eigenvalue is 2. They don't always work out quite so beautifully. Let's find the second eigenvector. In fact, I'm going to let you guys find the second eigenvector. So here's the equation we're going to do. I'm going to do -1, 2, -3, 4 times xy equal to 2 times xy. So I know I said I was going to let you guys do it. Well, go ahead. I'll give you like 30 seconds to write this equation. This times this equals that times that, and see what you get for x or for y. Yeah. 30 seconds, 40 seconds. So hopefully you guys all got something like 2, 3 as your eigenvector. Here's how I'm seeing it. Again, I'm isolating y, 2y equals 3x. Now, at this point, I personally like to just pick numbers. If I've got something times y equals something times x, I let x equal the coefficient of y and y equal the coefficient of x. So then my eigenvector is, well, x is going to be 2 and y is going to be 3. You can make other choices, right? You could have picked 4, 6, or negative, I don't know, 10, -15, right? Any multiple of any non-zero multiple of an eigenvector is also an eigenvector for that same eigenvalue. So, but what I should also point out is that if we solve this for y, you get y equal to 3/2 x. And the reason I mention this is because this line and this line are important lines. They're called eigenlines, and they are going to be important when we graph the direction field for the differential equations that we talk about later. So let's see. What else do I want to say here? So the reason we're talking about this is because it relates back to solving a system of differential equations, specifically this one. So here's what we've got. So let's say let's try and think of this as like an actual model of something. So let's say that x of t is the population of a predator, say wolves. Population of wolves. And y of t is a population of prey. Let's say it's deer. And here's what we're going to say. Dx dt, the rate of change of the population, is the growth rate of the wolf population. And similarly, dy dt is the growth rate of the deer population. Now, the thing about these is that they're interdependent, right? The wolf population depends on how many deer there are, and vice versa. The deer population depends on how many wolves there are. If there's a lot of wolves and not very many deer, well, the wolves aren't going to have a lot to eat, and so they're going to die off, allowing the possibly the deer to grow, or vice versa. If there's too many deer and not enough, not very many wolves, and the wolves are going to kill a bunch of deer. Okay, anyway, so here's our model. We're going to say that the rate of change of x, so dx dt, is equal to negative x plus 2y. So what this is kind of saying is that the growth rate of wolves depends on how many wolves there are, and the more wolves there are, the less fast it's going to grow. We're not kind of taking into account like them repopulating. We're talking about like them having enough resources, plus 2y. So the more deer there are to feed on, the more the wolves can grow. And in a similar way, dy dt, the growth rate of deer, is going to be negative 3x plus 4y. So again, the more deer there are, the more deer they make. The reason I'm giving like this, the reason this is like negative, right? The more wolves there are, the less fast they're going to grow, because they're competing for the food resource. Whereas the deer, we're not really saying that because they have like plenty of fields and grass to eat upon. Okay, but here's what we've got. And also I should say, right, and let's give ourselves some initial conditions. Let's say at time 0, there are 2 wolves and 4 deer, which I know is not very realistic, but whatever. Okay. Yeah, interesting. Okay. So we can rewrite this linear system of differential equations. That's what it is. This is a linear system of differential equations. The derivative of x depends linearly on x and y. The derivative of y depends linearly on x and y, right? There's no x squared or y cubed or natural log of it, right? There's nothing other than variables to the first power. So these are first order, right? Because there's only one derivative, linear differential equations. We can write this as a matrix. We can say that, do I have enough room here? Yeah, I might have. Let me just scooch this over a little bit. All right. X0 equals 2, Y0 equals 4. So we can write this as a matrix. We can say that the derivative of our vector, let's call the vector x, which is maybe why I should have called this x1 and x2. Sorry. This is equal, sorry, my notation is feeling not great here. Apologies. I guess I'll call it v. It's really common to call it x though. Sorry, let's call it v for a minute, even though I feel like it's awful. Is dx dt dy dt as a vector, but that's equal to the matrix of coefficients, -1, 2, -3, 4. times the variables x and y. So I want to make sure everyone's on board with this, right? This matrix multiplication just gives you dx dt equals -1 times x plus 2 times y. And the second one is dy dt equals -3x plus 4 times y. Great. Okay, well, yeah, I have to call this, I guess this is the derivative of the vector x, right? So yeah, sorry, I can't not call it dx dt. It's the derivative of the vector. So here's the thing. We know from earlier this class and in lecture day that if dx dt equals a times x, we get that x is equal to c e to the a times t. And that was our solution. So we're going to have the same idea, right? What we've really got here is that dx dt equals a matrix A times the vector x, right? This is the vector x. This is the vector dx dt. Okay, well, this sort of differential equation is going to have the same kind of solution, right? That dx as a vector dt equal to a times x. The solution is going to be that the vector x equals c e to the a times t. But you can't, well, I mean, it's not true. You can actually do e to a matrix. It's kind of a weird thing that you learn, that you probably won't learn, but you could learn in linear algebra if you took that class. You don't need to learn it, though. It's not that important. But the idea here is that instead of doing e to the a times t, we're going to use the eigenvalues. So what we're really going to get is the following. Yeah. Yes, sir. So we've got our eigenvectors. We'll come back to those in a minute. We should have more room on the board. So here is the idea, right? Instead of saying that the derivative of the vector x with respect to t is equal to, I'm sorry, that's not what I really want. That's fine. Is equal to, this is a times x. Instead of that giving us x equal to c e to the a times t, what instead we're going to get is that x, or x of t, which again is just xy as functions of t, that's going to equal the following. I'm going to use both my eigenvalues and my eigenvectors. So it's going to be c1 e to the lambda 1 t times the eigenvector v1 plus c2 times e to the lambda 2 t times the eigenvector v2. And this, and we're going to check it right now, this is the general solution to the equation dx dt equals a times x. How about that? Let me show you. So I'm going to remind you guys of a couple things. V1 and V2 are eigenvectors of A. So that means that A times V1 is equal to its eigenvalue times V1. And A times V2 equals the eigenvalue times V2. All right. So what's going to happen when I take the derivative of this thing? Right, this is x of t. I take the derivative of it, well, yeah, sorry, I had to make sure of something. So, right, if we take the derivative here, if I take dx dt, so I'm going to remind you, this vector is just a vector of constants, right? It's the vectors that we found, like, we're going to do it for the actual example in a minute, but this is just, these are just numbers, right? It's just like 1, 1, or 2, 3, or whatever. The only place there's a variable in this whole equation is right there and right there. So check out what we get. The derivative of c1 times e to the lambda 1t is going to be c1 times e to the lambda 1 t times lambda 1. And I'm a little bit worried this is going to go awry somehow. Make sure I've got this. We should back up a second. Now this isn't going to work out, but it's not going to be super illuminating as I thought it was. So let's go ahead and instead look at our actual example. So let's actually use our example and say that so what we had before, we have that x of t, y of t, which is what we're calling the vector x of t. That's going to equal c1, which we don't know, e to the lambda 1, which was 1 times t, times v1, which was 1, 1. Right? So I want to point out, sorry, this matrix is the same matrix we started with today, and we already know the eigenvalues and eigenvectors for it. The eigenvalues were 1 and 2, and the corresponding eigenvectors were 1, 1 for the eigenvalue 1, and 2, 3 for the eigenvalue 2. Are there any questions so far? I feel like I'm saying a lot of things here, so let me pause for a second and ask you guys if there's anything you need me to kind of revisit.
I want clarification. So the vector x of t is a representation of the original equations x and t of y of t?
Right.
Okay.
Right. And so our original equations were, I think I said them on the board. Yeah. So our original, well, so we don't actually know what they are yet, right? We're about to find them. So all we know, so really what I could write in this dx dt is negative x of t plus 2y of t. And dy dt is negative 3x of t for y of t. So just like when we were solving dx dt equal to a times x, and we were trying to find what x was as a function of t, now we've got these equations and we're trying to find both what x and y are as functions of t. And the answer is right here. We just have to make it look a little bit nicer. And specifically, we need to find those constants c1 and c2. Luckily, we have some initial conditions. We know that x of 0 is equal to 2, and y of 0 is equal to 4. So the one thing about finding the initial condition, the constants here, is it's not quite as easy as the previous one. You actually have to do a little bit of work here. So if I plug in t equal to 0, I'm going to get 2, 4 equal to, luckily t equals 0 is easy. E to the 0 is 1, e to the 0 is 1. So I get c1 times 1, 1 plus c2 times 2, 3. There is a number of ways to solve a system of equations like this. You can go straight to saying 2 equals c1 plus 2c2, 4 equals c1 plus 3c2. And I'm a fan of when I see the same coefficient, do like this equation minus this equation. So 2 minus 4 is negative 2. C1 minus C1 is 0. 2C2 minus 3C2 is negative C2. So that's going to give me C2 equals 2. And then plug that back in here. 2 equals C1 plus 4. So subtract 4. 2 minus 4C1. So C1 is negative 2. Really, though, do whatever works best for you. Some people like to write this as a matrix. You can do like, 1, 2, 1, 3 times C1, C2 equal to that, and then multiply both sides by the inverse of this matrix, whatever floats your boat. Okay, so here's what we've got. We've got a lot, but we have the solution to the system of equations. So our solution is the following. Where'd you go? X of t, y of t, which we could write separately, but we usually write them together. which is the vector x of t. And again, apologies for the kind of wonky notation. Sorry, this is equal to, and you're going to want to memorize this formula. It's going to help a lot. C1 e to the lambda 1 times v1 plus C2 e to the lambda 2 times v2. Right? This equation right here. This is your bread and butter. This is your solution to a lot of things. So in this case, we found C1 to be -2. We found C2 to be +2. So our solution is -2 e to the 1 times t. You don't really need to write the 1, but okay. Times the eigenvector 1, 1 plus 2 times e to the 2t times the eigenvector 2, 3. To be a little bit more clear, what we're explicitly saying is that little x of t is -2 e to the t times 1 plus 2 e to the 2t times 2. And y of t is -2 e to the t times 1 plus 2 e to the 2t times 3. Those are our solutions to the system of equations. And you could even, so you don't have to check this, but if you actually, so we could though, right? So let me show you. So let's see what dx dt is. Dx dt is the derivative of this. So it's -2 e to the t plus 2 times 2 is 4. Derivative e to the 2t is 2 e to the 2t. So it's going to be 8 e to the 2t. I hope everyone's okay with that. And if you look at, so that should equal -x of t plus 2y of t. So if you do negative this plus twice this, so let's see, negative this plus 2 times this. So that looks, oh yeah, so +2 plus 2 times -2 is -4. So 2 minus 4 is a -2 e to the t. Awesome. And then this negative this plus 2 times this. So you get a -4 plus 2 times 6 is 12. -4 plus 12 is an 8 e to the 2t. So it really is the solution, right? If you do -x of t plus 2y of t, it is equal to the dx dt. And similarly, our dy dt would be, the derivative of this is -2 e to the t plus 6 times 2 is 12 e to the 2t. And if you did -3 of these plus 4 of these, you would exactly get this, right? -3 times -2 plus 4 times -2 is 6 minus 8, which is -2. And -3 times 4 is -12 plus 4 times 6 is 24, and -12 plus 24 is 12. Okay, so great, we found the solution. Something that people often like to ask about this is what happens to the populations. So what happens to x of t and y of t as t goes to infinity, as time goes on and on and on and on and on? Well, and this feels like, oh yeah. Okay, so yeah, so in this example, right, you got a negative thing and a positive thing. So if I let's say the limit as t goes to infinity of -2 e to the t plus 4 e to the 2t, e to the t is going to infinity. So is e to the 2t. That's a negative infinity, that's a plus infinity. Which of those is bigger? Yeah, which infinity is bigger? They're both super big. Say again, sorry.
E to the 2t.
Right, that's the bigger one. So this infinity is bigger than that one. So this is going to infinity. Another more precise way of showing this is you can factor out e to the t. And so you've got e to the t times -2 plus 4 e to the t. And then you can say, oh, that's going to infinity times that's also going to infinity, and infinity times infinity is going to infinity. And the same thing is true for this one, right? The limit as t goes to infinity of -3 e to the t, sorry, -2 e to the t, apologies, plus 6 e to the 2t is again going to go to infinity. So both these populations are getting infinitely large in this particular setup, which probably isn't very realistic, but hey, that's life. So what I want, so with that, got the wheel on my toe. Okay, sorry. So what that means though is that both these populations are kind of unstable, right? There is no stability place where you can get to like there being 10 wolves and 6 deer all the time. And let me show you, where'd you go? So yeah, let me share this one. So I use the GeoGebra phase plane, which is definitely linked in Canvas. On the, I think on the modules page. So if the cool thing about this, I plugged in my equations, negative x plus 2y and negative 3x plus 4y for x prime is equal to that, y prime is equal to that. And what's kind of cool is you can pick any starting place, because definitely people are going to ask you, like, if we start with this initial population, what's going to happen? So if we start with, well, let me see, we started with how many wolves and how many deer? I think it was 2 wolves and 4 deer. That sounds right. Yeah, 2 of x and 4. So if we start at the point 2, 4, which is maybe a little off the grid, I think we can zoom out though. And can we redo it? We zoom out. So if you redo it, it's going to get you back to the original function that they started off with. Terrible. Let's plug this in real quick. I forgot my equations already. I think it was, sorry. Now everything's gone away. Where'd my equations go? Trying to show you guys something cool. It went away. Let's see where my equations go. Negative x plus 2y and negative 3x plus 4y. Oops. Yeah, I don't want that yet. So you do that, it gives you the phase plane. And then you can, oh yeah, this is, I can, so if you wanted to, you could say, I want to start when there are 2 of x and 4 of y, which is about right there. And then you can see, oh yeah, in that case, both x and y are getting really, 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 really large. But if we had a different initial condition, like if we started over here at say 3 wolves and 1 deer, then it's looking pretty bad for everybody, right? If you go this way, you're going to get essentially 0, right? Everyone's going to die out because it's going, right? Both x and y are going towards negative infinity. But no matter kind of where you start, there is no stability. And again, it's not a super great analogy because, right, you can't have a negative number of wolves, but okay. That's kind of the idea, is that we're going to be looking at these phase planes and saying like, oh yeah, if we start at this point, are we going to have some stability and get closer to some particular value, or are we going to have some unstable thing and go far away? There's something else I wanted to show you, and I guess I will do that. So there are multiple tools for graphing things. There's also there's a couple Desmos ones I think I've linked for you guys. Yeah, this one's kind of all right. But if I, oh wait, this one is not so all right. This is not one. Yeah, this one's less awesome. Never mind. So I will tell you, these are fine. The one I really like though is the p-plane one. Yeah, which is not here, which is somewhere in my computer, which I don't remember. Anyway, what I'm trying to say is that if you graph the eigenvectors, the eigenlines, y equal to x, and what was the other one? Y equal to, I think, 3/2 x. 2x equals y equals. Yeah, it was y equal to 3/2 x. So there's y equals x, and kind of here is y equal to 3/2 x. There's kind of this line of where if you're exactly on that line, it is stable. If you're anywhere off of it, it can either be stable or unstable depending on what kind of situation you have. Okay, we'll do more with that later, but I feel like that's not kind of the main thrust of what we're doing. So let's kind of go back a little bit. And that was the end of that example. Okay. So the equilibrium or steady state for this particular problem is 0, 0, right? If there's 0 wolves and 0 deer, there will always be 0 of everything. Nothing will change. But any other initial condition, it's gonna be unstable, right? Because we saw this in the graph, it was moving way away from the middle. Let's go ahead and what's time here? We got 9 minutes. Let me see. So let me see if I've addressed everything with this. I didn't want to completely ignore that worksheet. Excuse me, that I was asked about. So let me take a look at it real quick. So I feel like what we did should be pretty sufficient for your worksheet. That said, I'm certainly happy to talk about an offset. Let's go ahead and just do another example. So let's say we've got this system. I want to solve the system of equations dx dt equals x and dy dt equals 4x minus y. With initial conditions, x of 0 is equal to 2, y of 0 is equal to 10. Okay, so interesting. So side note that I was not aware, this problem models what's called commensalism. I'm not familiar with that word. It looks like it's kind of called wrong. Where one species benefits from the other but causes no harm to it. For example, suckerfish or barnacles. So, right, essentially, yeah, that's kind of cool. So like this is the species that's being is the helper out, and this is the one that's like the suckerfish. So okay, yeah, interesting. So let's set up a matrix. So we have that in matrix form, dx dt, dy dt equals coefficient of x, coefficient of y, coefficient of x, coefficient of y times x, y. That's what we got. Now, I want to point out, here the eigenvalues are extra super easy to find. Whenever you have a 2 by 2 matrix where this spot is 0, or this spot is 0, or both, the eigenvalues are just the elements on the diagonal. So our eigenvalues here are lambda 1 equals 1, and lambda 2 equals negative 1. That is always true. If either of the off diagonals are 0, then the diagonal elements are your eigenvalues. We could also use the method I talked about, right? The trace of this matrix is 1 plus negative 1, which is 0. And the determinant of this matrix is 1 times negative 1 minus 0 times 4. So then using the quadratic formula, we know that the eigenvalues are going to be the trace plus or minus the square root of the trace squared minus 4 times delta all over 2. So that's going to be 0 plus or minus the square root of, let's see, negative 1, 0 minus 4 times negative 1. So that's going to be 4 over 2. So that's plus or minus 2 over 2. That's plus or minus 1. Just like we said. You shouldn't do this work for this kind of problem because it's way easier to be like, hey, look, I can see the eigenvalues, so can you. Sorry, so someone sent a message. You said that if I didn't say if the diagonal is equal to 0. I said if one of the off diagonal things. So here are 3 matrices where I can read the so like this matrix and this matrix and this matrix A0 BC, AB 0C, A0 0C. All of these have the eigenvalue A and C. As long as this is 0 or this is 0 or both, the eigenvalues are just going to be the diagonal elements. Cool. Okay. Yeah, we got time. So now we got the eigenvalues. Let's find the eigenvectors. So the eigenvectors are going to be, let's see. So we do our usual thing. We do A times V1 equal to lambda 1 times V1. To find the eigenvector, let's see, my matrix is that 1, 0, 4, -1 times the vector that we don't know yet, which I'm going to call, I'm going to call xy, even though I've already kind of used xy equals 1 times xy. Okay, so here's something interesting. If we use the first equation, we get 1 times x equal to x, which doesn't seem super helpful, right? Because x could be 1 or anything really. So let's look at the second equation. Second equation would be 4 times x minus y equals y. Okay, that's a bit more helpful. Because then we have, let's see, negative 2y equals negative 4x, or y equals 2x. So my eigenvector would be, well, the choice I would make would be to say that x is 1, y is 2. And then for the other eigenvector, let's erase this over here because we don't really need all this. For lambda equal to -1, we have 1, 0, 4, -1 times xy equals to -1 times xy. So that's going to give me x equal to -x. Ooh, what does that mean? Anybody know?
0.
Right. And you can either be like the only number that's own negative is 0, or you can add x to both sides. Okay, here's the thing. If you get x equal to 0, you don't have to do any more work. If x is 0, what does y have to not be? Right? If x is 0, y can't be 0. So what would you like to have there? Well, I'd like to have 1. But you can pick 5 or 6 or square root of 2. But all those vectors would be multiples of each other, so they're all eigenvectors. I'm going to pick 1 though, because that's a pretty standard choice. You could use the second equation if you want. If you do that, you get 4x minus y equal to -y. The y's cancel and you still get x equal to 0. So it's not really helpful. You have to know that if you do an equation where you get one of the variables equal to 0, that automatically means the other one is going to be not 0, and we specifically like to choose 1. All right, so here's my system of equations. Or I should say, here's my solution, really. My solution is that the vector, and you guys really do want to memorize this, it's going to come up a lot, is C1, like as you forget, what it is, C1 e to the lambda 1 t plus C2 e to the lambda 2 t. And specifically here, it's x of t, y of t equal to C1 e to the lambda 1 was 1 times t. Oh, so I forgot the V1. I forgot the eigenvectors. So it's C1 e to the 1t times 1, 2. I know we're out of time, but let me just finish that. Well, C2 e to the lambda 2 was -1t times V2, which was 0, 1. And then we'd have to solve for the constants, right? So we have to use the fact that, what have we got here? We have, we know that our initial conditions were 2 and 10. So by plugging t equal to 0, I get 2, 10 equal to C1 times 1, 2 plus C2 times 0, 1. Because the e to the 0 part just goes away. This one's especially easy to solve for because you got a 0 there. That says 2 equals C1 times 1 plus C2 times 0. So 2 equals C1. And then, so that's 2. And then 10 equals 2 times 2 plus C2. So 10 equals 4 plus C2. So C2 equals 6. So our final solution is, and let me just write it in here since we're out of time. Our final solution is that this is 2 e to the t times 1, 2 plus 6 e to the negative t times 0, 1. And here's what I want to say. The long-term population here, well, as t goes to infinity, x of t is going to go to infinity, I think, right? Yeah. And as t goes to infinity, y of t also looking like infinity, because this is going to go to infinity and this part's going to go to 0. I feel like it's not really the question you want to be asking, though. I guess I should stop talking. Want to say more stuff. So we'll continue with this example on Friday because there is a little bit more to say about it. And we will sketch, yeah, we're going to sketch our own direction field for this. But then we'll also look at the one that's computer generated. So that's where we'll go. Because what we really want to, so what we want to talk about at some point is where we have equilibria and where we have like stability, where we have instability, which we're definitely getting to. Yeah, that's all I got. Actually, that's not all I got. One more thing. What we're gonna see is that whether a system is stable or unstable completely depends on the eigenvalues, whether they're positive, whether they're negative, whether there's one of each, whether they're real or whether they're imaginary. So we're going to learn that if you can see what like when eigenvalue is positive, when eigenvalue is negative, you're like, oh, I know what's happening there. Or if they're both negative, I know it's stable. Or if they're both positive, I know it's right. There's a whole thing. We'll talk about it later.